We're going to solve this fun radical equation from the 1990 Mu Alpha Theta math competition. We have that the square root of x plus 1 equals x minus root x minus 1. All we want to do is find all real solutions. Give this one a try yourself. If I had to give you a hint, maybe I'd say get rid of the radical by squaring the equation and watch out for extraneous solutions. Grab a cup of coffee and let's solve this problem.
Coffee time math with Wrath of Math.
All right, now I am ready and raring to go. Let's get right into it. When you notice that we have square root of x and x in this equation, you might think to try some variable substitution. Say y equals square root x, and then y squared equals x, so we could rewrite this equation as a quadratic in terms of y. But I'm going to opt for what I think is a slicker method, although you could do that and it would work. Notice that our radical terms are the same except for their sign. One's positive and one's negative. But if we isolate them on the same side of the equation, we'll easily be able to get rid of the radicals. So if we add the square root of x to both sides of the equation, here on the left we'll have 2 square root of x, and then we'll subtract 1 from both sides as well. So we'll get rid of that plus 1. We'll have x minus 1 minus 1, so that's x minus 2. Now we can square both sides of this equation in order to get rid of the radical. Doing that will give us 4 times x is equal to x minus 2 squared, which is x squared minus 4x plus 4. Now we want an equation equal to 0, so we'll subtract 4x from both sides, and that's going to give us x squared minus 4x, which is minus 8x, plus 4 is equal to 0. I might think for a moment about factoring this equation, but I can't think of any numbers that multiply to 4 and add to negative 8, so I'm going to skip straight to applying the quadratic formula. Applying the quadratic formula gives this: x equals negative b, which is 8, plus or minus the square root of b squared, which is 64, minus 4ac, which is just 4 times 1 times 4, which is 16, all over 2a, which in this case is just 2. Okay, so what is this equal to? Well, we can break up this fraction. We have 8 over 2, which is 4, so this is equal to 4 plus or minus this square root over 2. 64 minus 16 is 54 minus 6, which is 48. So it's 4 plus or minus the square root of 48 over 2. Now, we can mess with this square root a little bit. What's 48 equal to? Well, 48 is equal to 4 times 12, so we've got some perfect squares that we could take out of this radical. 48 is equal to 4 times 12, and 4 is a perfect square. However, 12 has another factor of 4 in it. 12 is equal to 4 times 3. So we could rewrite this as 4 times 4 times 3, or 4 squared times 3. So we had 48 under the radical. We rewrote that as 4 squared times 3. Now we can go ahead and write this equation again. So it's equal to 4 plus or minus. We can take the 4 squared, since it's a perfect square, we can take that out of the square root as 4. Then we would have 4 over 2, which is 2, so we have 4 plus or minus 2 times the square root of 3. 3 is all that's left in the radical. And so we have 2 possible solutions to this equation. X equals 4 plus 2 root 3, and x equals 4 minus 2 root 3. They could both be solutions to the equation, but we have to check. We've got to take each one and plug it back into the original equation to see if it works. Because when we squared both sides of this equation, we may have created an extraneous solution. So one of these might be an extraneous solution. We've got to check to make sure. Let's start off with 4 plus 2 square root of 3 and see if that does indeed satisfy this equation. If we wanted to use calculators, that'd be kind of boring. Of course, we could just punch this into the calculator to see if this is equal to this. If we want to do it without a calculator, it would be helpful, since we have the square root of x in this equation, it would help us to verify its truth with this x value if we could identify what the square root of 4 plus 2 root 3 is. Written in that form, that's not very useful. One method that can work to find the square root of an expression like this is to be optimistic and hope that the square root of this has the same form. So perhaps the square root of this is a plus b root 3. The same form as 4 plus 2 root 3. We just need to figure out what a and b are. If we square both sides of this equation, we can place some constraints on a and b that will help us solve for them. Squaring the left side of the equation gives us 4 plus 2 square root of 3. Squaring the right side of this equation gives us a squared plus 2ab root 3 plus b root 3 squared, which is 3b squared. Now, in order for a and b to satisfy this equation, the coefficient here next to the square root of 3 must be the same as the coefficient we have on the left for square root of 3. So 2 times ab must be equal to 2. Again, the coefficients of the radical terms must be the same. This, of course, implies that AB is equal to 1, and without doing any further exploration, that gives us some ideas for integer solutions of A and B. We could have A equals 1 and B equals 1, or we could have a equals -1 and b equals -1. Thankfully, though, we can immediately discard these negative possibilities because this is the square root function. It's the principal square root function, which means it's taking the positive square root. If a and b were -1, well, that would be a possible negative square root, but we're not interested in that. This is the principal square root. It's a function, so it has one definite output, the positive square root. So we can forget about those, a equals 1 and b equals 1. Now those might work, but we haven't finished satisfying all the conditions here. We also need to pay attention to the non-radical term. So a squared plus 3b squared, the non-radical terms here, a squared plus 3b squared should equal the non-radical term on the left, which is 4. Now, does a equals 1 and b equals 1 satisfy this equation? Well, that would be 1 squared, which is 1, plus 3 times 1 squared, which is 3. 1 plus 3 is 4, so hey, that works, and we found a way to rewrite this square root into something a little nicer. The square root of 4 plus 2 square root of 3 is equal to 1 plus 1 times the square root of 3, which is just 1 plus the square root of 3. Now that we have this nice expression for x and this nice expression for the square root of x, because remember that's what this is, the square root of x, we can go ahead and test to see if it satisfies the original equation. The left side of our equation is square root of x plus 1, so that's going to be 1 plus the square root of 3, that's the square root of x, plus 1 is equal to x, which is 4 plus 2 square root of 3, minus the square root of x, which is -1 minus root 3, minus 1 minus root 3, and then we have a minus 1 on the end. So is this equation true? Well, on the left, we have 1 plus 1, so 2 plus the square root of 3. On the right, we have 4 minus 1, so that's 4 minus 2, which is 2. And then we have 2 root 3 minus root 3, which is just a single plus root 3. Hey, look, that works. 2 plus root 3 does equal 2 plus root 3. So we have found a real solution to the equation. X equals 4 plus 2 square roots of 3 is a solution to our original equation. Now, all that remains is for us to check the other solution, the other possible solution, 4 minus 2 root 3, and see if that works as well, or if that's an extraneous solution. So now let's investigate x equals 4 minus 2 square root of 3. Again, we'd like to find a nice expression for the square root of x. So that's the square root of 4 minus 2 square root of 3. And again, we would like to think that it has a form like a plus b times the square root of 3. Now, of course, we already figured this out for a very similar expression, 4 plus 2 times the square root of 3. In fact, for that previous square root, we found that it was equal to 1 plus 1 times the square root of 3. So here we would think maybe we just have to flip a sign or two and we should have another valid square root. So maybe 1 minus the square root of 3 will work. Would that work? Well, we'd have 1 times 1, and we would have negative root 3 squared, which would be a plus 3. So we would get that 4 term, and then we would have minus root 3 minus root 3. So yeah, that would work. However, 1 minus the square root of 3 is negative. Again, remember, this is a square root function. It has a definite output. That single definite output is the principal square root, the positive square root. So it's not 1 minus the square root of 3 we want, but in fact, multiply that by negative 1, square root of 3 minus 1. That's what we want. And again, you could square this and see that it works. You'd have square root of 3 times square root of 3, which is 3, plus negative 1 squared, which is plus 1, so you'd get that 4. And then you would have root 3 times negative 1 plus negative 1 times root 3. That would be your minus 2 root 3. So indeed, the square root of 4 minus 2 root 3 is root 3 minus 1. We can go ahead now and check our original equation with x equals 4 minus 2 root 3. On the left, square root of x plus 1. What is that? Well, we know the square root of x is root 3 minus 1. Then we have that plus 1. This is equal to, or is it, x, which is 4 minus 2 root 3. 4 minus 2 root 3 minus the square root of x. So that's minus the square root of 3 minus negative 1, which is plus 1, and then a minus 1 at the end. Here on the left, we have minus 1 plus 1, that's 0, so all that's left on the left is the square root of 3. On the right, we have 4 plus 1 minus 1, which is just 4, and then we have minus 2 root 3 minus root 3, so that's minus 3 root 3, and that doesn't look right to me, but we'll just be sure. Add 3 root 3 to both sides, and we get that 4 root 3 is equal to 4, and so the square root of 3 is equal to 1. Oh wait, that's not true, so that was an extraneous solution. So although 4 minus 2 root 3 was a solution to the quadratic equation we set up, turns out it wasn't actually a solution to the original equation that we were interested in. And so the only real solution is x equals 4 plus 2 square root of 3. And that's it.
Subscribe for more of the swankiest math videos on the internet.